to this new edition of the Colloquia of the IAC. Today it's our pleasure to have here Justin Reed, who is visiting under the UNDARK project. And he's going to stay this week, but he's coming back in August if you are interested in talking to him. Of course, many of you know Justin. He was graduated from Cambridge in 2004. He held postdoctoral positions in Cambridge, then in ETH Zurich. Then he came back to the UK with a lectureship in Leicester. Then he was professor in ETH Zurich until he was offered to chair a professorship in Surrey, where he is now, where he has also been the head of the department. Of course, we know him because he has been working in a lot of things that are of interest to us, to the IAC. He is an expert on galaxy evolution information, particularly in the local group. He's a famous dynamicist, the main developer of a very famous code, GraphSphere, but he's also well known for his work on the simulation front. So he's going to talk about many of the things, I believe. And of course, it's a pleasure to have you here, all an honor. So the floor is yours.
Thank you very much. Great. And it's so nice to be back and see so many familiar faces. I was trying to do the math on when I was last here, and it's embarrassingly long ago. I feel like the pandemic has erased at least 2 years from my life. This is weird green haze, post-pandemic just disappeared. But it's so nice to be back. And I want to talk about some of the latest works that's been emerging from a now long-running project, which I lead. It's an international collaboration between multiple partners across the world now, called EDGE, where we're trying to simulate the very smallest galaxies at a sort of extremely high resolution, with the goal of trying to understand more deeply how galaxies form, how galaxy formation impacts dark matter distribution in these systems, but also maybe to begin to understand the formation of dense stellar systems like globular star clusters. And that's what I'm going to try and get to in the talk today. So what do I mean by that? Well, I've been interested for quite some time in understanding the origin of these two rather different stellar systems. So on the left, we have a dwarf irregular galaxy, WLM, and this is one of the least dense objects in the universe, okay? I'll just pop up its vital statistics here. So it has a stellar mass of about 10 to the 7 times the mass of the sun. It has a half-light radius of 1.3 kiloparsecs, and as best we can tell by modeling the motions of its stars and gas, which is something that people like Giuseppina Battaglia have really led on here at the IAC, we can figure out that it's almost entirely made of dark matter all the way from its middle to its edge. And we can compare and contrast that with this globular cluster on the right here, one of the most massive Milky Way globular clusters, Omega Centauri. That has a stellar mass of about 4 times 10 to the 6, so it's just under half of WLM, but its size is substantially smaller, just 5.8 parsecs across. And there's no evidence so far that this object contains dark matter, but of course it's very difficult to detect dark matter in an object that has such a high stellar density. And if you look at the ages of the stars in these systems, WLM has been forming stars continuously through to the present day, but its oldest stars are as old as WLM. So somehow the universe conspired to make these two very different objects, or was beginning to make these two different objects at the same time. And how could this be? Okay. And we can see this also more quantitatively on a plot like this. This is showing on the y-axis the absolute V-band magnitude, and on the x-axis now half-light radius in parsecs. So these are now measurable, directly observable quantities. And I've just put up a load of data points on here for globular clusters, shown in gray, and dwarf galaxies, shown in green. And when I started my PhD many moons ago, these were two very well separated populations, right? So the received wisdom was globulars live over here and they're small and bright, and dwarf galaxies live over here and they lie roughly along tracks of constant surface brightness. But you can see that with the advent of modern surveys and more data, these two populations start to bleed into one another, and there's now this area in between where actually, at least just using this plot alone, it's not entirely clear which of these are dwarf and which of these are globular clusters. And that's got even more interesting with the advent of these objects down here that have been found over the past few years at exceptionally low V-band magnitude. And these could be an extension of the globular cluster track or an extension of the dwarf track. And just using this plot again We really can't tell. But it matters, right? Because one way, first of all, it matters because we'd like to understand how these different objects form. So it matters from a galaxy formation perspective, but it also matters from a cosmology perspective. And one way we can constrain the nature of dark matter, for example, is by counting galaxies, right? And then we count all the dwarf galaxies. The more galaxies we find, the colder the dark matter should be. But if I can't tell what's a galaxy and what's a star cluster, then I can't count galaxies, right? If every single one of these is a dwarf galaxy, I'm going to get a very different inference on the nature of dark matter than if none of these are dwarf galaxies, okay? So this raises a whole bunch of questions that I want to kind of try and tackle in this talk. And that includes, how do globular clusters form? Do some of these globular clusters contain dark matter? Do they all contain dark matter? Did they used to contain dark matter, right? Because if they contain dark matter, I should probably count them like I count my galaxy. What are the objects in the overlap region where GCs and dwarfs cohabit the size luminosity plane, and can I tell the difference between them? And those are the three main things I want to try and address today. Now, ultimately, these questions will probably be answered with data. Data is king. But I'm a theorist, so I want to try and get some insight from the theory side that we can then apply to the data to make progress, okay? And the tool we're going to use for that is the one I alluded to right at the start of the talk, which is our edge simulations. Engineering dwarfs at galaxy formation's edge, so the whole name is recursive. And it's a collaboration, it was a collaboration between Lund, UCL, and Surrey, but the key collaborator at UCL, Andrew Ponson, has now moved to Durham, so it's now a collaboration between Lund, Durham, and Surrey. And also many of our former members have spread off around the world, so I really should start adding more logos. We have representatives at Bath, the University of Hertfordshire, Carnegie Mellon in the Carnegie Observatory, sorry, in the US, and you name it. So it's a sprawling collaboration. And I should say up front, we are people power limited in this collaboration. So we have really, really fun simulation data and not enough people to poke about at it with sticks. So if there's anything you would like to do with the edge data, please do let me know. As long as the project isn't already being done by somebody else, fill your boots. Okay, so what's special about Edge? Well, I think one of the special things about Edge is that we take a slightly different approach to how to model galaxy formation than has been done in the literature in the past. And we call this a bottom-up approach. Now, before I get into what the bottom-up approach is and why it's different, I should probably just give a very quick primer on what we're doing with this whole galaxy formation malarkey in the first place. So when we want to study galaxy formation, we need to do it in the context of some structure formation model, some cosmology, okay? And luckily, the universe gives us a pretty good idea of what it looked like when it was very young. So about 400,000 years old, we have a snapshot of the universe at that time gifted to us by the cosmic microwave background radiation. And here's the data from Planck, where the Milky Way has been carefully subtracted, and you're left with this sort of speckled egg. And these tiny temperature fluctuations at about the 1 part in 10 to the 5 encode information about density fluctuations in the early universe. So we have a pretty good idea of what the universe looked like at that moment, but only on large scales, because this is not sensitive to the very smallest scales. So we've got a pretty good idea of the large scale universe, but the smaller scales are affected by things like what is the precise nature of dark matter. And so by assuming different dark matter models, we get different small scale power. And if we want to figure out which of those dark matter models is correct, we need some other data to figure out whether that small scale power was right or wrong. And that's one of the usages for these simulations. But it means that we need to evolve this early universe through to the universe today, where we do have data on smaller scale structures and we can test and compare those models. Now, because the process of structure formation is what we call nonlinear, all that means is that at some point, different regions of the universe that are just happily collapsing all on their own start to fall together and merge. And at that point, the system of equations is nonlinear. And so we can't just use perturbation theory or whatever. Perturbation theory will get us from about redshift 1000, that's the CMB, to about redshift 20. But beyond redshift 20-ish, we kind of need to use simulations. So that's where the simulations come in. It's a wonderful simulation black box. I could give a whole talk on just this. But lucky for you, I'm not going to do that. But if you're really interested, we can absolutely get into that. Love that. But there's some simulation magic that then involves these. So you're solving the equations of coupled equations of gravity for your assumed dark matter model and the Euler equations for your gas hydrodynamics. And then typically you'd include some prescriptions for gas cooling, star formation, and what happens when stars explode and so on. So that's all the physics that goes in. And then you get some kind of hopefully realistic looking galaxy. Here's showing the gas density living in some dark matter halo. And then we can compare that to observations. So it's a real galaxy with a wind. This one also has a wind. And then, you know, depending on how this comparison goes, we can make inferences about both galaxy formation and cosmology. And if we keep going around this loop, we gradually learn more and more about galaxies and hopefully more and more about dark matter and the universe as a whole. So that's the basic idea, but of course, the simulations are imperfect, okay? And in particular, they have limited spatial or mass resolution. And that's what I'm showing in this plot. So whenever you set out to start your simulation, you're going to have a choice. And you're going to have a trade-off between how big a patch of the universe you're going to model and what fidelity, resolution you're going to model that giant patch of the universe at. And I've shown that on this plot here. This is, I'm sorry if your favorite simulation is not on here. This is a relatively recent compilation. So this is some representative example of simulations in the literature today. And on the y-axis, we have M gas. This is sort of the optimistic, probably, minimum gas mass you think you can resolve. And on this axis here, we have the volume of the simulation, okay? So huge volume simulations over here and tiny, tiny volume simulations over there. So up in this corner, we have large volume, low resolution simulations, really useful for getting galaxy statistics. And so you have, you know, Eagle and Illustris living up here. And then down in this corner, we have Lyra, where they model just a few galaxies at very high resolution. So we're getting down to below 10 solar masses per gas element. But the price you pay is you can't model very much of the universe, okay? And this correlation is basically exists because of the finite power of computers, okay? Now, obviously, in an ideal world, so here we have great resolution, here we have great statistics. In an ideal world, we want to be here in this corner, right? We want great resolution and great statistics. But we can't do that yet. And in our drive to get to this corner, there's kind of two different ways we could get there, right? We could come down, so we take Eagle and Illustris, we keep raising the resolution and we march down here. Or we could take something like Edge, which is sort of quite high resolution and low volume, and just model ever larger patches of the universe. And this is what we mean by bottom up. Now, once you arrive in this corner, surely it doesn't matter, okay? But I would argue that in your journey to this corner, there is a difference between these two approaches. And the reason there's a difference between these two approaches comes down to a thing that we call subgrid physics, okay? That at any given resolution, there's a bunch of stuff that I don't resolve. This is always true, right? It's true for all of these simulations, okay? There's a bunch of physics that I simply don't capture. Now, if I'm only modeling gravity, this is fine, right? Because gravity, at least in standard, you know, Newtonian weak field gravity, is a scale free. There's no scale in the problem. So I can go bottom up or top down, and it genuinely makes no difference. And I'll show you an example of that in a minute. But the minute I want to actually model galaxies, now I've got gas cooling and star formation and feedback and so on. And depending on my M gas, different kinds of physics become resolved. They move what we call above the grid, okay? So you can imagine at this sort of resolution, this is 10 to the 6 solar masses. That means that one gas parcel of gas is almost as big as all of omega Cen. I'm not going to learn anything about omega Cen from these simulations up here, but also my prescription for forming stars is going to be some phenomenological model to produce whole omega Cens, right, when I form stars. Whereas down here, I'm below 10 solar masses, I can actually almost spawn individual stars. So my subgrid model is going to look very different, okay? And so the whole issue here is that if I go this way, every time I go up in resolution, I need to change my subgrid model. And that's fine, but it's going to make it difficult to converge, right? I could get radically changing results as I move down the page. Here, my subgrid model is completely fixed because I'm not changing my resolution. So I can fix my subgrid model and just model ever bigger systems and gain more insight that way. And the advantage of this approach really kicks in if there is some magic scale where we think we can get a qualitative shift in how well we can reproduce galaxies. And I believe there is such a scale, and I'm going to try and argue for what that scale is. And that's the scale. That's why Edge sits here and not below and not above. Okay. So but let me just show you a couple of pictures of top down versus bottom up. First, so here's the beautiful Aquarius simulations that you've probably seen many, many times. This is a beautiful example of top down, where top down is perfectly appropriate because you're only modeling gravity. So here we have a dark matter halo of about the mass that would host a sort of Milky Way galaxy. This is in classic cold collisionless dark matter. So you see all these little blobs of dark matter down to the resolution limit of the simulation. This is actually one of the lower resolution Aquarius simulations. If you go to higher resolution, it looks like this. And you see a really beautiful convergence as you go up in resolution between the low resolution and the high resolution run. This tells you that we know how to solve gravity. We know how to solve what we call pure dark matter simulations. The big challenge is how you put stars and gas and so on into this thing in a reliable way. But of course, when we add stars and gas, that beautiful convergence is much harder because you go from lower to high resolution, and now you've got to change your subgrid model. So in EDGE, we take this bottom-up approach, and what we do is we start with a low-resolution patch of the universe, a void volume. This is the volume from which we draw all of our EDGE galaxies, and we deliberately pick a low-resolution patch because we want to focus all of our resolution on a small number of objects, and if those little objects encounter big objects, then we would have to stop our simulation because we can't resolve the big object with that much resolution, at least not yet. And then we pick a few representative points from this volume at a given mass, and then we zoom in the resolution on these points, leaving the rest of the void at low resolution so we get the right tidal field. And that allows us to get down to extreme resolution here, sort of 100 solar mass, roughly 3 parsec type resolution. All right, so where does our resolution for EDGE come from? I'm going to give you 2 arguments for the resolution in EDGE, and the first is purely observational, okay? Now, I think it's relatively established that the key thing that regulates galaxy formation is feedback, right? And feedback, at least for the smallest galaxies, which is what we're focused on in EDGE, feedback from stars, okay? And what that feedback from stars means is that, you know, when massive stars are born, so sort of O, A, B type stars, they produce stellar winds that return metals, momentum, energy to the interstellar medium, but they also inject energy through the winds and momentum. And then at the end of their lives, the most massive stars, above about 8 solar masses, will explode in a supernova, and that returns even more energy, metals, and momentum to the surrounding ISM. And finally, of course, you have photons coming from those stars, which can ionize the gas around the star-forming region. So these are all different types of stellar feedback. And we know that what this feedback does, although this is all happening on very, very small scales in star-forming regions, when you have correlated star formation, the combined effect of the feedback from all those stars produces hot bubbles, and those bubbles overlap to drive galaxy-wide winds. And this is a sort of a bit of a poster child for this. This is M82. It's a relatively massive dwarf galaxy. You can see the disk here with dust. And we can observe this galaxy-wide wind blasting off from this galaxy. And these winds then become a sort of natural galactic thermostat. So you can imagine if I form more stars, I get more feedback, right? And that feedback will act to push the gas out and suppress the formation of more stars, okay? But if then everything quietens down and gas cools again, I get star formation again. So you know, the less feedback I have, the more stars I form, but the more stars I form, the more feedback I have. So it's a natural regulator, okay? So if you want to get galaxies right, I think the key, or the sort of minimal requirement, is to try and understand and capture these winds. So what we wanted to try and do in EDGE is have these sorts of winds be above the grid, be an emergent phenomenon, not something that we put in by hand. And that means we need to resolve the impact of feedback from individual stars. And that's happening on much smaller scales than this. This is 2 kiloparsecs, but the origin of the energy and momentum that's driving this wind is star-forming regions that are much, much smaller. Now, we can't zoom in on star-forming regions in M82, but we can see them in the much closer Large Magellanic Cloud. So here's a close-up view of a star-forming region, 30 Doradus, in the Large Magellanic Cloud. Again, this is all real data. And you can see these beautiful hot X-ray bubbles, right, interspersed with cold regions that are still forming stars. So within this 50 parsec stamp, now much, much smaller scales, you have both star-forming gas and hot bubbles coexisting. And then presumably these bubbles are what overlap to drive galaxy-wide winds. So just eyeballing this picture, if you want to try and capture the physics of what's going on here and then get this to drive a galaxy-wide wind, then your sort of resolution requirements are going to be something like what's in the box, right? You're going to have substantially better spatial resolution than 50 parsec, let's say 10 to be optimistic. You need a good mass resolution to go with that. You're going to have to capture high density gas, because this cold gas here is high density, and of course it's cold, so you're going to have to get to below 100 Kelvin. So these sorts of requirements observationally motivate our choice in EDGE to aim for roughly 100 solar mass resolution, and sub 10 parsec resolution, we actually go for 3 parsecs. The second argument is the overcooling problem. And this is something that, again, is not new. It's well known in the field. But this is basically that, well, let me illustrate it with this picture here, right? So suppose I have a grid code. This is true also if you have a particle-based code, by the way. It's just easier to illustrate with the grid-based code. So with the grid-based code, you're modeling your galaxy and you chop up space into these cells, and then you have a smallest cell that sets your spatial resolution. Now let's imagine that my smallest cell is 100 parsecs across, which is still pretty good, right? And I have a density threshold for star formation of about 10 atoms per cc. Now this, though, however, is like a half of that 30 Doradus region. So inside this little cell, what's really going on in the real universe is something like this, right? There's a star-forming region, it's forming individual stars. Each of these flickers is an individual supernovae. Multiple supernovae overlap to drive these bubbles, and all that's happening below the grid. That's what we mean by subgrids. We're not resolving any of that. So if I want to do some kind of stellar feedback, I'm going to have to build some phenomenological model for all of this happening inside that cell. And the trouble is, if I just take, say, a single supernova, for the sake of argument, and I deposit its energy in that cell, okay, at this density, then what I'm doing is I'm taking the supernova energy and I'm smearing it over a large chunk of 30 Doradus, which is clearly physically incorrect. And not only is it clearly physically incorrect, it causes a problem. Because if you just do the sort of back of the envelope math and you say, okay, I'm going to take 10 to the 51 ergs, typical supernova energy, and I'm going to smear it over a cell at this density, and it's an ideal gas, then you get a cell temperature of a couple times 10 to the 4 Kelvin. Why is that interesting? Well, that's very close to the ionization temperature of hydrogen, right? It means that hydrogen gas can cool incredibly efficiently at this temperature through atomic line transitions. So if you heat the gas up in this cell to this temperature and you have a model for gas cooling, then your hydrogen gas will immediately radiate that energy away and cool right back down again, which means your supernova is doing nothing, which means you get no regulation effect, you get no galaxy wind, and your galaxies come out all looking wrong, okay? Now, we've known about this for ages. It's called the overcooling problem. You're getting too much cooling, and therefore your feedback is not doing anything, and therefore you're not getting your galactic thermostat. And so your galaxies just end up with far too many stars, and they all end up looking like blobs, and it doesn't work. So there are lots of solutions that have been proposed to this, relevant to simulations at this resolution or below. And Claudio's done some beautiful work on this as well. And there are lots of different ideas. So some simulations switch off cooling for a time. Some deliberately inject more energy. Some inject momentum directly instead of energy. And these are all completely valid things to do at this resolution. And you can argue cogently that if you don't do it, it's definitely worse. But in terms of predictive power, it's not clear which of these choices is the best one. And you might worry that whatever choice you've made, it's fine, but you don't know that it's going to give you a realistic galaxy at the end for the right reasons, okay? So in EDGE, we take a rather inelegant brute force approach of solving this problem by just going to very high resolution, okay? And so there's some beautiful early work done by Kim et al., where you can model single blast waves, a bit like this. It's actually a whole little star cluster, actually. But you can do control experiments like this and figure out what's the minimum resolution I need to get to resolve the momentum driving from these explosions, okay, without having to switch off cooling or do anything else. And it turns out that that's about 10 parsecs. And so we go in EDGE for 3 parsecs to be, a little bit ahead of that. So this is another main reason why we chose this resolution. And finally, you might say, well, why not go to even higher resolution? Well, first of all, of course, it's really expensive. So you don't necessarily want to run very expensive simulations, but also the danger of going to even higher resolution is that then you start getting snarled up in the physics of how individual stars form. And we explicitly wanted to avoid that Pandora's box. Okay, so there's a kind of a sweet spot, I think, around 3 parsecs where you can resolve the impact of individual exploding stars while avoiding getting into the messy physics of star formation itself. So star formation is prescribed in EDGE, right? So there is a subgrid model, of course, but we can tune the star formation model on star forming regions. And then if galaxies come out looking right, that is not a circular argument, and hopefully we're making progress. So that's the idea. Oh, and by the way, if you do the same back of the envelope here, this cell would be 10 to the 6 Kelvin, and 10 to the 6 Kelvin is way past the peak of the cooling curve. It's still too low temperature compared to 30 Doradus, but it's high enough to solve the overcooling problem. Okay. All right, so that's EDGE. What does it look like? All right, so I'll cut to the chase. This is an example of one of our EDGE dwarfs. We have our fiducial resolution here, 3 parsec spatial, baryonic mass resolution about 160, and then we have a higher resolution version where we go to slightly higher resolution in MBAR and much higher resolution in MDM for a subset of our simulations. This is showing the density as a function of time for our lowest mass dwarf that survives reionization. So at much lower mass than this, around about redshift 8 or so, reionization kicks in. These are ionizing photons that come from the rest of the universe and bathe the whole universe in photons. That ionizes all the gas, and if you're too low mass at that time, you can't cool your gas anymore and form any more stars, so you become dead. But if you're just a little bit more massive, you can hold on to your gas through reionization and carry on forming stars, and that's what this little galaxy does. You can see it's highly dynamical. I didn't put the redshift counter, unfortunately. I think we're still around redshift 1 this year. You can see that at this resolution, we're actually forming little gas clumps that form little stellar clumps. These explode to produce bubbles and holes. And if you look at the H1 gas in nearby tiny dwarf irregular galaxies, it really does look qualitatively similar to this. And it's on our shopping list of things to do to actually do that comparison more quantitatively. But this kind of messy bubbled ISM is real. You can see that at late time, it starts to settle down into more of a rotating structure. And you're getting these winds coming off that are above the grid. You know, they're emergent and they're driven by correlated feedback from multiple star-forming events in the galaxy. And the mass of this object is actually very, very low. So as I said, this is the lowest mass object to survive reionization. It actually has a halo mass of about 5×10 to the 9. It forms just under 10 to the 7 solar masses in stars. And it's actually remarkably similar in many ways to galaxies like Aquarius, probably a little bit less massive than WLM, which I showed you at the start. Yes? Yeah, I'm going to show that in a minute. So I'll show. This is the lowest mass that survives reionization. So we have lower mass galaxies, but they don't form stars after reionization. Yeah, so I'm going to show you that now, actually. But before I get into actually, quantitative comparisons with data, I should point out that there's actually now, oh, I didn't mean to do that. There's actually now 3 flavors of EDGE. There's EDGE 1, which is most of the stuff I've just shown you, EDGE 2 and EDGE 3. Now, I said at the start, the whole idea with bottom-up is that you fix your subgrid physics and never change it again. But, there's still always subgrid physics choices, and there's still subgrid physics choices in EDGE, and there's still physics that was missing that we wanted to add. So with each iteration of EDGE, we've tried to improve our model by adding more physics. So in EDGE 1, we had this high resolution. We had a model for 1A and 2 feedback stellar winds reionization. We tracked iron and oxygen. We ran a couple of simulations with radiative feedback from stars. So we have reionization, of course, bathing the whole box, but this is actual photon feedback from individual stars. We did everything in cold dark matter, and we only got up to about 10 to the 9.5 in halo mass. Then we won a lot more computer time for EDGE 2, which allowed us to be more ambitious. So we had non-equilibrium chemistry. Radiative transfer was included as standard in all runs. We tracked 8-element chemistry. We improved the yields. We improved the reionization model. So compared to the latest data constraints, we ran some models in warm dark matter, which I would love to show you, but I won't get into that today, but they're really interesting. And we got a little bit higher in mass, up to 10 to the 10. And we're just beginning our campaign for Edge 3, where we're beginning to explore the impact of black holes, varying yield models, what happens if we spawn star by star rather than having 300 solar mass star particles, the impact of POP3, and, going to much higher mass, where we want to get up to, actually our highest mass one is actually 610 to the 10. So we're hoping to get to sort of small Magellanic type objects if you're au fait with the local group. And it'll probably take a couple of years for those simulations to finish. So, just giving you a hint of what's coming, okay? So how do the simulations do? They are extremely expensive, okay? There's a price to going to this high resolution. And the reason they're so expensive is that when one star explodes, so remember, we're trying to capture the impact of each individual exploding star. So when a star explodes, we're depositing 10 to the 51 ergs in our now 3 parsec cell. That heats the cell up to millions of Kelvin. So you have very hot and very dense gas, which means you have a very high sound speed. Now, there's a thing called the Coulomb condition, that the time step in my simulation must be short enough that sound waves don't escape from my cell in one time step. So when I have a very, very, very high sound speed, I must have a very, very small time step. So the time step in these simulations can shrink to 300 years per time step, and we're running for 14 billion years. So it's expensive. And it's sort of unavoidably expensive, I think. So these simulations take a long time. What that means is that we couldn't tune any of our subgrid model parameters, right? So we made our best guesses for what we thought they should be. We did do a sensitivity study where we vary them by large numbers and see what happens. But basically, what you get is what you get, okay? And this is what we get. So this is the scaling ratios. Now, you can get a sense of how uncertain we are due to our subgrid model choices by simply comparing Edge 1 and Edge 2. Edge 2 has a quite different subgrid model. We think it's quote-unquote better, but if you like, it's just different. And so here's M star versus M halo. Here's some data constraints based on Milky Way satellites, okay? Here's some data constraints based on nearby gas-rich dwarf irregulars, okay? And here are all the simulations, right? And you can see that both Edge 1 and Edge 2 look pretty good in this space. There's some hint maybe that Edge 2 is forming a few too many stars at high mass, okay? But otherwise, it looks perfectly reasonable out of the box. And that plays out also in all the other observable scaling relations. So here we have the size luminosity plane where I started the talk, and you can see that our dwarf galaxies overlap the data very nicely, but not just reproducing the existing data, we can begin to actually make some predictions. We're predicting new kinds of objects, particularly here at very low surface brightness. And I'll talk about those in a minute. And there's an interesting object here, very, very dense. This is actually a nucleated dwarf. And if I have time, I'll get back to that at the end of the talk. You can look at gas, and you see a very nice thing here that, again, we overlap the data very well, but you see this beautiful transition around M star of 10 to the 7, where these objects have a pretty stable H1 gas mass, but at lower mass, you have this highly variable H1 gas mass due to feedback, due to repeated cycles of bursty star formation. And then at the lowest mass, most of the objects are H1 dark. This is actually, we think, very important. We have a paper coming on this soon. If you want to do cosmology by counting galaxies in H1, right, instead of photometrically, you're going to need to take this into account because, for large chunks of their lives, some of these galaxies will be invisible in H1 at a given survey depth, right, unless you get down to sort of here. And so this variability will need to be taken into account, and that's something that we're looking at right now. And finally, you can look at the mass metallicity relation. And in fact, our very first Edge paper, we showed that this is the most sensitive relation. You can really do violence to your subgrid model and still reproduce most of the other relations I've shown you. So an optimist would say that means that, galaxy formation models are doing really well and it doesn't matter what I do with the subgrid models. And a pessimist would say there's just no power in any of the other data I've shown you. But this is a very informative plot. So if you change the subgrid physics, you're very sensitive to this. And the intuitive reason for that is, so this is V-band luminosity versus mean metallicity. The intuitive reason for this is that the galactic thermostat does a pretty good job of keeping your stellar mass pretty much the same. And I mean, if you completely switch off the thermostat, of course it fails. But as long as you have some kind of feedback thermostat, then you can kind of really change your subgrid model. And all that happens is you form more stars and then you get more thermostats. So it all kind of regulates out and turns out okay. But the feedback that's coming off is carrying with it metals. And so if I have more violent outflows, I carry away more metals. And that means that pound for pound, I have a lower metallicity for a given amount of star formation. Conversely, if I have weaker winds, the metals are more easily retained and I enrich faster. So you can kind of move, so the slope comes out about the same, but if I change the strength of the feedback, I move orthogonal to this relation where stronger feedback is 2-metal poor and weaker feedback becomes more 2-metal rich, okay? Unfortunately, it's not quite that simple. You can also move in this space by changing the yield model. And in Edge 2, we had stronger feedback, in fact, because we've included RT, but we also changed the yield model. And the net result is actually Edge 2 is slightly better than Edge 1. But maybe there's some tension up here at the higher mass. Again, we didn't tune it to get this. We were just trying to make things better. They do seem to be slightly better. Edge 1, you could argue either the yields are a bit wrong or the feedback is perhaps a little bit too strong. One of those two things. But still, you know, not far off the actual data. And again, it's what we get out the box without tuning. So that's comparisons to existing data. But if theories are going to be useful, we shouldn't just be chasing real data and showing that we can reproduce real data. We should make predictions that can be tested by observers. And that's when we really know we're making progress. So I want to spend the rest of the talk talking about predictions that we get from these edge simulations, some of which are being tested now, some of which will be tested actually, hopefully not too far from now. So the first thing is we predict a host of new kinds of dwarf galaxies. And in order for me to explain this, I do need to explain one more thing about EDGE, which I hadn't discussed yet. And that is that we use this rather special initial conditions generator called genetics that was invented and developed by Andrew Ponson. And what genetics does is it allows us to forensically change the initial conditions without violating cosmology so that we can take the same dwarf and we can make it form earlier and later. And in fact, with new versions of genetics, you can even change the angular momentum of the dwarf, you can change it, you can tweak its mass. And so the advantage of this is you can do controlled numerical experiments, right? So you can take different dwarfs in different mass bins, and then for each dwarf, you can explore independently of mass the role of assembly history, right? And this is very important for us in EDGE because we can't afford to run at this kind of resolution very many dwarfs. So by independently exploring assembly history and mass, we can get much more inference into which drives what process of galaxies faster while running a very minimal subset of dwarfs. So that's the kind of idea. And here's an illustration of how this works. You start with a default model, you engineer it to form a little bit later in this case, and you do that in practice by lowering slightly its density at early times. And that now becomes what we call a later former. And if you look at the movie here, right, there's this merger here that's going to happen. And that's going to merge in there. And you can see over here, it hasn't happened yet. Okay. So basically what it's doing is, this is, by the way, an example of one that is snuffed out by reionization. So that's why it all goes dark. So you can see that by engineering it to form a little bit earlier or a little bit later, I can independently explore that dimension versus mass. Okay. And that's going to be quite important to understand the next plots. So what does that look like quantitatively? Well, so here's one dwarf that we've kind of played that engineering game on. So this is showing its mass assembly history. So the halo mass versus redshift. This is today. This is the early universe. And all the dwarfs arrive at the same point here. They all arrive at the same final mass because they've been engineered to do so, but they assemble at different rates. In the background here, you see the 68, 95% confidence intervals of the assembly history of all dwarfs in the parent edge void volume. So that's just showing you that none of these engineered dwarfs are 2 sigma unreasonable, right? So we have this one is forming sort of just about 2 sigma early. This one is forming just about 2 sigma late. And these two are kind of 68% typical, right? But what you can see happening here is this one forms late, this one forms early. And just by changing this assembly history, we get a radically different stellar mass. So the early former has nearly 10 to the 6 in stars, and the late former is 310 to the 3. Well, no, a little bit of that. So it's just over 10 to the 4, sorry, by here. Okay. Now, why is this? This is all because of reionization. So this X marks the epoch of reionization quenching for each of these for each of these dwarfs. So it's when star formation is shut down by reionization. Now, the reason this is all at slightly different times is because the epoch of reionization quenching is slightly different from the epoch of reionization. So what reionization does is it ionizes all the gas. You can think of that like switching off the tap so that no more gas can flow onto my dwarf galaxy, okay? But if it already had a bunch of gas, it can still limp along forming stars from that cold gas until it's done, okay? And so you get slight variations in the quenching time depending on how much cold gas you had at the moment that reionization switches off the tap, okay? And that means that typically these dwarfs limp along forming stars till about redshift 4, even though reionization is at higher redshift than that. Okay, but what it means is if you're very massive, like this one, before reionization, then you can form lots of stars because basically the more massive you are, the faster you form stars. So this galaxy is forming stars like the clappers, and then reionization comes along and it's done. But this fella has barely formed before reionization comes along and zaps all the star formation. So there's lots of little pieces that form a few stars. Reionization kills all of them, and this galaxy actually then builds up through the late dry mergers of all these little reionization relics, okay? And that makes it very much lower stellar mass, but it also gives it rather different observational properties. So this is an early forming ultra-faint dwarf, and this is a late forming UFD. And the late forming UFD, as a result of forming through these late dry mergers, ends up being very, very much puffier, much, much more extended, and much, much lower surface brightness. So if we go back to our V-band half-light radius plane, here's this same galaxy, and as it forms later, it moves to lower and lower and lower surface brightness until it drops below 31 mags per arcsecond squared. And here we have now a prediction that there should exist these, what we call ultra-faint, ultra-diffuse galaxies. So combining those two ideas, very, very low surface brightness, the reason being that they build up through mergers. Now, there are galaxies here. There's Homo and Torrealba. They're slightly different than this one. But it's not clear if these galaxies are there because of tides. So to be clear, we're predicting that this thing should exist out in the wilderness, in the middle of nowhere. And you can test this prediction as well, because if you form this thing through late mergers, because you're forming it from all these lower mass pieces, it has a systematically lower metallicity at a given luminosity than a similar galaxy. So if you do find one of these things, you've got that extra check. What's the metallicity? Is it systematically low? What other predictions do we have? Well, those are our lowest mass dwarfs in Edge that get zapped by reionization. So now, instead of moving in assembly history, let's move in mass. So we're going to move up in mass a little bit now. So these are now different dwarfs where we go up in mass. So the lowest mass one here, this is just over 10 to the 9 solar masses. This is still an ultra-faint dwarf. Okay, so 10 to the 9 is roughly the halo mass scale at which we have reionization relics. Okay, so this one just still a classic ultra-faint dwarf. Gas is all ionized, no H1, about 10 to the 5 solar masses in stars, typical thing, right? But now let's just go up a little bit in mass, okay, to here. Now we're just over 2 times 10 to the 9. And now what starts to happen is that ionized gas in the UFD here can start to cool, but it doesn't have long enough to start forming stars. So this galaxy will form stars in the future, but has not yet formed stars today. But it now does have detectable H1 gas. So this is now a gas-rich ultra-faint dwarf, no young stars, but with H1 gas. So we predict there should be objects that look like UFDs, not forming stars, but they do have H1 gas. And if we go up in mass just a tiny little bit again, from here to here, now, that small difference, there is enough time for that H1 gas to cool and start forming stars. And so the galaxy rejuvenates, starts forming stars again. And you can see that in the star formation history here, where you have the pre-reionization star formation, a long hiatus, and then it grows in mass at late times. And now that all that gas can cool and it starts forming stars again. Okay. And these kind of rejuvenators with a burst, a gap, and a burst. And this gap, by the way, of course, will have everything from almost undetectably small to extremely large with just a tiny bit of young stars. All those things are possible just depending on when this galaxy grows in mass enough to start cooling and forming stars, okay? So this is an example where the gap is quite large. And interestingly, this system at the end is forming stars at a remarkably low rate. So it's about forming one star every sort of 100,000 years. And there is a galaxy we know like that, and we're finding more of them, and that's Leo T. That's the lowest mass star-forming galaxy in the universe, a very puzzling system, and this is a really great candidate for galaxies like Leo T. Maybe Leo T is exactly one of these rejuvenators. So we predict gas-rich UFDs, we predict rejuvenators, and we predict ultra-faint, ultra-diffuse. How am I doing on time? Oh dear. We make lovely predictions for dark matter heating too, but you know, I think am I gonna skip over that? Do you want to hear about dark matter heating or globular clusters? All right. Okay, well, I skip over that. Blum, blum, blum. Dun, da, da. Anyway, dark matter heating is a thing, and Ariana's predictions were correct. That's the short. That's the short answer for that. And there's some additional refinements due to lovely work by Claudia Mooney. Please do check it out and talk to me afterwards. All right, let me get to what I really wanted to get to before the end of this talk. Okay, so I've shown you the gas in EDGE, but I've not shown you the dark matter or the stars. So here's another movie now showing the dark matter and the stars forming in EDGE rather than just the gas, okay? And what you can see, you could kind of see it in the last movie with the gas, that the gas forms these dense clumps, and then, of course, stars form in those clumps. So at this kind of resolution, we are actually getting clustered star formation. Okay, and some of these blobs have dark matter, and they're just, you know, satellite dwarfs of dwarfs, if you like. But quite a lot of these blobs are actually forming without any dark matter. And so we do actually have, at the same time, dark matter free, well, dark matter rich sort of dwarfs of dwarfs, but also dark matter free globular cluster-like candidates, okay? And so there's this beautiful work that's been led by my PhD student, now postdoc, Ethan Taylor. So please do check him out. There's Ethan. And this paper is coming out very soon. So watch this space. It's just about being accepted. So we can now return to the size luminosity plane that I showed you right at the start of the talk. Here are all the edge dwarf galaxies we have so far now in the triangles, okay? And they do indeed lie roughly along these tracks of constant surface brightness. And I've colored the points here by their dark matter content, okay? So if they're yellow, they have basically no dark matter. And if they're black, they're all dark matter, okay? So all these objects are dark matter rich, and you would probably classify them as dwarf galaxies. But over here, look, we have pure star systems, and they are distinct, right? They live in a different part of this space, and they start to overlap the globular cluster distribution. These are our 5 surviving globular cluster candidates across our EDGE simulation suite. And this separation between these two populations is not just apparent in the size luminosity plane. I'll show you in a minute. It's also apparent in other observational planes. But before I get to that, you can see that now actually we can start to talk about what's going on in this overlap region. And it's interesting that some of our dwarfs are encroaching into globular cluster territory. So maybe some objects here are in fact dark matter rich, and we might want to think a bit more carefully about how we do that separation. But I'm also going to try and convince you that these objects down here are not just an extension of the more massive dwarf galaxies, but they're a new class of objects in their own right that we call globular cluster-like dwarfs. Now, before you panic, you can't see a third class of object in this plot. You're going to see it in the next plots, okay? But you can't see it in this plot either, okay? Don't worry. So now let's look at metallicity luminosity. And again, you can see that the dark matter rich objects lie along this track, the mass metallicity relation. There's a pretty good correlation between the two things. But our globular cluster candidate objects scatter above this relation and don't show such a correlation. And again, that's consistent with globulars that live up here and dwarfs that lie along this track. So we're getting realistic sizes and luminosities, but also realistic metallicities. And finally, the icing on the cake is we can start to look at dynamical mass and metal and age spread. And this is where we start to see actually a new class of object emerging. So if you look at the dynamical mass here, this is some estimate of like the sort of dynamical mass to light ratio. Also, this is just dynamical mass, sorry, and this is stellar mass. So if you have no dark matter, you should lie along tracks of this equaling this. So this is a unity along here. And that's where our globular cluster objects lie. So they have no dark matter and they lie along this track. And real globular clusters lie along this track too, okay? Dwarf galaxies, super dark matter rich, and they live up here with loads and loads of dark matter. But then notice these objects here in between, they sort of have intermediate dynamical mass, something in between globulars and dwarfs, maybe a third class. And you see it even more clearly over here what's going on. So here I'm showing the age spread versus the iron spread. And again, here we have our globular cluster type object, very low age spread, and an iron spread of less than 0.2 dex, again, consistent with what we know about globular clusters. Dwarf galaxies over here, much larger age, delta age. So this is the minimum maximum age difference in the stars, and a much larger iron spread. But then there's these objects. Right? In many ways, they start to look more like globular clusters than dwarf galaxies, but they do contain dark matter. And these are what we call our globular cluster-like dwarfs. And what's going on here is really a story of quenching. Who shuts down your star formation? These objects don't have dark matter. They form, and I'll show you some pictures of this in a minute, they form inside somebody else's dark matter halo. And because they don't have their own dark matter halo, when they start to form stars, the stellar winds on their own can be enough to shut down star formation, and certainly one supernova is enough. And this time scale here is roughly the time for a single supernova or two supernovae to go off. You're kind of rolling the dice on when the supernova go off, so it's not an exact time, but it's about here. So these things are basically quenched by one supernovae or even just stellar winds. But these objects, these do sit in the middle of their own dark matter halo. So they're like a single star cluster sitting in the middle of its own dark matter halo. And that surrounding dark matter halo allows them to hold on to their gas just a little bit longer. So a single supernova is now not enough to shut them down. They need multiple supernovae, but multiple supernovae are enough to quench them. So they self-quench. They don't need reionization or anything else. They shut themselves down, and that's it. And that means that some of them form stars long enough to have a slightly larger metal spread than the globulars, but many of them have a metal spread very similar to globulars and an age spread a little bit larger, but it would be hard to measure. Okay. And dwarf galaxies, by contrast, they live in much more massive dark matter halos, and nothing can stop their star formation. Well, they can't stop their star formation by themselves. Something else has to come along and stop the star formation, and that's reionization. And if you get to the most massive dwarfs, not even reionization can do the job, and they just carry on forming stars. Okay, so galaxy formation at this mass scale is really a story of quenching. Yes.
Most galaxies have what we find they merge as the most globular cluster-like dwarfs.
Oh, that's a great question. I haven't actually checked that. I haven't actually checked. I should check. I imagine some of those mergers probably are. Quite possibly. Yeah, quite possibly. We haven't looked at that because we were looking for surviving globular cluster-like dwarfs, and we rejected anything that had gone through a merger. Yes, exactly. Exactly. The surviving ones are the tritus that never encounter anything else, and we have like 6 of those in the simulation. So okay, so I'll finish with some pictures of what I'm talking about. Here is a couple of globular clusters forming. The fun thing with the globular clusters is they don't all form in the same way. There's at least 2 different ways that they form. And all the different ways people have talked about globulars forming in the literature, I think probably everyone's a winner. It's all going on in the simulations to differing degrees. So this is what we call sort of regular star formation now. Don't forget, this is at high redshift, so regular star formation is messy, like I showed you in the gas movie, right? So just focusing on this red one, you can see all the stars are forming in clusters. But here's just one example. You have star formation, regular star formation occurring in this dwarf. A star cluster forms, and it's just forming where all the other stars are forming along this top track. Sorry, this is the top track. So you just have regular star formation, and there's our little globular cluster, and it's just lying in the distribution of all the stars that form. And this one is very unlikely to survive to redshift 0. It's in a very dense environment. It will probably be destroyed. Here's a different scenario. Now I have 2 galaxies that are merging, and the gas in between them gets compressed and enriched by outflows. That excites star formation in the compressed gas. So this globular is forming far away from the rest of the stars, okay? And these ones are much more likely to survive to redshift 0. So 4 out of 5 of our surviving globulars form in this mechanism and not that. But it's about 50-50 in terms of birth, but about 80% in terms of survival is the bottom one. And here's just a picture of one of the GCDs. Very different story. Now we have a little dark matter halo. Gas flows in, you get a little burst of star formation, stellar feedback, and that's it. Okay, so that's one of the GCDs. And the GCDs are fascinating because they are the lowest mass objects that form stars in our simulation, and they're forming in halos that are 10 to the 7. So they're quite rare. These have to be unusually dense halos at 10 to the 7. But we've looked in our warm dark matter simulations. Now, 10 keV is my back of the envelope calculation, but I can tell you for a fact that our 6 keV simulation, which we've actually run, has none of these. And we're actually going to go to higher temperature now and see really where the dropout is. But these objects don't exist in warm dark matter because the halo that hosts them doesn't exist. And because it's a very low mass halo at very high redshift, it's actually very sensitive to dark matter temperature. Okay, I think I'm going to have to stop there. I said there's also beautiful nuclear star clusters that live up here. So do check out Izzy's paper. That's already on the archive if you want to know all about nuclear star clusters and the beautiful and distinct color magnitude diagrams they have, and the fact that omega Cen is probably one of them. And that's interesting for dark matter too. But I'll leave it there and put up my summary. Thank you.
Okay, thank you, Justin, for the very interesting talk. So we have many questions. Let's start with Arianna.
Great talk, thanks a lot. So how do you test your predictions? Because you're finding galaxies that are like, you talk about a couple of different galaxies, like one that is gas-free, very low surface brightness, and so it's at the same ultra faint and ultra diffuse. So how would you observe that? But also I didn't quite, I mean, that's one question. The other question, which is related, I didn't quite get why this globular cluster like dwarfs are a separate class of galaxy. It just seems to me that you just get to the edge where you can form stars. You go down and down in your dark matter halo, you form stars that do not seem to have qualitatively or quantitatively different characteristics compared to the rest of the dwarf you showed. I mean, just you colored them in a different way, but otherwise,
yeah, so I'll take the...
I'm sorry, very final thing.
Yeah.
That's on side. So you start at the beginning defining your simulations in voids to avoid all the... So how realistic is to compare to the real universe in which we know that galaxies do not live in voids?
Yeah, so all very good questions. So what was the first one again? Oh, how would you observe? Yeah, okay. Yeah, so we have a project trying to do that now. So observing them out in the wild might be really difficult because it's 31st mags per arc second squared. But the hope is that we haven't calculated the statistics of these things. That's on our shopping list of things to do. So we have a semi-analytic code called DarkLight, which we've trained on Edge so that we can apply Edge-like physics to the whole void volume, and then we can do statistics. So we could also apply it to Milky Way volume. So that's all coming. And when that work is complete, we'll be able to say how many of these objects would we expect around the Milky Way. Now, if that number is not negligible, we might hope to see something like this in the LSST footprint. If we need to really look for it at several megaparsecs, then it's going to just be hard. You know, I suspect there will be objects like this that get accreted onto the Milky Way, and then the trick is really finding the ones that have not been mushed about by tides too much, so that you can be certain that you're looking at something that's pristine, right? And that is definitely going to require new surveys, however you look at it. So that's that one, and we are actually looking for them in, you know, whether there's any of them that might have come in with the Magellanic Clouds, because we know the Magellanic Clouds are on first infall. So if we can find something associated with the Magellanic Clouds, then again, it might be pristine or more pristine. So that's one tactic. The second point was about the separation into a third class. Yeah, so we had a lot of debate within the group about this as well. I think that there is a theoretical distinction, right? Because about quenching, basically, that they're low enough mass that they quench themselves, and that means that they are just one star cluster living in the middle of one dark matter halo. And in the past, people have talked about that as a distinct pathway for forming globular clusters. So there's form in the literature for saying, actually, this is what globular clusters are. And there are other groups that are even saying that. What we're saying is single star clusters do form in their own dark matter halo, right? But they actually are observationally distinct from globular clusters. So this isn't the way to explain globular clusters, I don't think, but it could, but it is a separate object, right? So it's a separate object theoretically from a quenching point of view, and the fact that it's a single star cluster in a dark matter halo, but observationally, it actually has measurable properties, not in every space, not in every observational plane, But in certain planes like delta age, delta metallicity, and dynamical mass, they are distinct from both globulars and dwarfs. And that means that there are observational ways to go and find these objects. And if you can find them unambiguously, then you will know that there is this object that formed in a 10 to the 7 solar mass halo at high redshift. So you get these beautiful constraints on dark matter. So those are all the reasons why we felt they deserve a separate class. Okay. And then the third point, what was the third point again? Void. Ah, yes, yes. So we picked a void volume. Yeah, there's not much I can say to that really, other than we obviously at some point we'll start to model these things in denser environments, and we'll see. But other groups are doing work on this. Alison Brooks's group, for example, has done lots of work comparing voids to not voids, and there are differences. You know, our ultimate goal is to compare these galaxies to galaxies in voids. So I don't know who will get there first, whether we'll get to modeling denser environments or we'll actually see ultrafaints in voids first. But when we can see ultrafaints in voids, then we can do a more apples to apples comparison anyway.
Yeah, okay. Well, just to respond to Aliena briefly, you do get galaxies in voids. You get fewer galaxies in voids, but there are galaxies in voids. Justin, super cool talk, very exciting. This is like the holy grail to resolve globular cluster formation. At least for me, it's my holy grail, right? I've got a lot of questions, but maybe we can talk about them offline. But so one thing, so the differences between the dark matter free and the dark matter globular clusters, you said there are observational consequences and you showed them. Did you calculate what your expectations for the mass to light ratio, you know, just say the virial mass divided by the luminosity of these objects? Because I ask, because we have data for massive galaxies now, so the high mass regime, for mass to light ratios for these objects, and we're seeing a bimodality in the mass to light ratios. So we're seeing a population of globulars which have mass to light ratios of about like Milky Way globulars, 1.5 or something. And then you're getting a population which look more like Omega Centauri, so a mass to light ratio in V band of about 2.5, but with a distribution of masses. So it's not clear that what these secondary objects are, but perhaps, or perhaps not, they're something completely different. We're seeing a population of objects which do have this elevated, they have an extra matter component which we would not predict perhaps.
That's fascinating. We should definitely talk about that offline. I think if there's a connection to anything I've shown here, it probably won't be the GCDs, because our GCDs are very low stellar mass. They're nothing like Omega Cent. But one of the things I didn't have time to show is we do form nucleated dwarfs, and those nuclei look very similar to Omega Cent. So it might be that you're seeing the nucleus of a dwarf and you can't see the host dwarf because it's too faint.
So a nuclear star cluster which is coming in and being stripped.
Even just you're literally seeing a dwarf galaxy, but you can only see the nucleus.
Interesting. Okay.
So we'd have to see whether your observations are good enough to rule out that.
We don't go too far down the luminosity function, but we need to look. Okay, cool.
Nacho.
Thanks for your talk. I have two questions. I will start first with the one that you didn't say much about the dark matter heating. So normally when thinking on the cusp core transformation, we have in mind that 10 to the 6 solar masses in stars is kind of the one that can regulate or not with the feedback, the transformation or so. I was wondering first whether with your new simulation, that regime of 10 to the 6 still state, or whether you are able to transform caps to cores from feedback to lower stellar masses. So what do you find?
Yeah, so I had a great debate with Ariana about this as well. We find that, so first of all, cusp core transformations is not a binary thing, right? It's a continuous heating process. So we find that all of our galaxies have some cusp weakening. So the minute the stars start forming, they start weakening the cusp. So even our ultra-faint dwarfs can have a central dark matter density slope that's shallower than -1, even though at the same time, none of our reionization fossils form a completely flat core. Okay, so that's the first point. And then the second point is we find actually even at a fixed stellar mass or a fixed halo mass, you get quite a bit of scatter because it depends how you form those stars. And if you form those stars in a more bursty manner, and if the underlying halo you're forming them in is already quite fluffy, say lower concentration, then it's easier to form a core. And conversely, if you have a very dense concentrated halo and you form all your stars all at once rather than in this burst mode, then it's harder to form a core. And there's a lovely paper by Claudia Mooney, it's on the archive, where she comes up with an observational proxy that kind of balances those two things. And she shows that if you just plot the ratio of the mass and stars formed before reionization to afterwards, that correlates very well with whether or not you should have a core or not. Now, I don't know if that holds to more massive galaxies, but certainly it seems to work for our low mass edge dwarfs.
Okay, so let me phrase it differently. If you find an ultra-faint dwarf 10 to the 4 with a core in dark matter, can you rule out your simulations with just pure cold dark matter collisionless, or do you think that still there is some room that feedback able to? So what kind of observation would you make to reconsider the cold dark matter scenario?
Well, so, you know, as I say, we do have an example of cusp softening, even, you know, that late forming one, right, which has less than 10 to the 4, there's a few 10 to the 4 stars at the end, right? That has a central dark matter density a factor 2 lower than its dark matter only counterpart. So there is a heating effect, but none of the you know, if you tell me there's a definite completely flat core in an ultra faint with 10 to the 4, even 10 to the 5 stars, that would be hard to explain with these simulations. I'm not going to say impossible because edge is not the truth. It's good, it's not the truth. So maybe there's something missing still, right? But that would be a challenge.
Okay. And finally, the second question related to the globular cluster ages, because you didn't mention about absolute ages. For example, we find plenty of globular cluster format with the age of the universe, basically 13 giga-years or so. Yeah. So we don't see any kind of, so we see many of the globular clusters very old. Maybe there are some examples of younger, I don't know. So I was wondering whether in this simulation where you propose 2 different mechanisms of formation, what kind of absolute ages do you expect to find for these objects?
Yes, that's a good question. So we haven't actually looked at whether the 2 mechanisms produce a delta age. If you look at the histogram of ages of all our globular clusters at birth, like when they're forming, there's no bimodality there, right? So they're all old, and the peak, I think, is around redshift 4. Checking my paper. The GCDs form earlier. So the GCDs form before the globulars on average. Some globulars are forming then, but most GCDs form around redshift 10. And then the globulars form a little bit later because they're forming inside something else that has to form itself, right? So globulars tend to peak around redshift 4-ish. It's the epoch of globular formation. And then we know globulars are bimodal. So the second mode, if any of this is correct, is presumably happening in something else, late galaxy mergers, much more massive systems, nothing to do with this.
Okay, one last question from Jorge.
Okay, very inspiring talk, really. And I have many questions, but I will focus on just one. Related to the globular clusters, one of the kind of characteristic properties of the globular clusters is the fact that you have multiple stellar populations, coeval, very different stellar composition. So how this fit in your modeling, your scenario?
Yeah, that's a great question. So the problem with multiple stellar populations is it means multiple things. So within the umbrella of multiple stellar populations, we should probably subdivide it into different categories. So there are what I would call abundance anomalies, right? So the actual observable is that there are weird anti-correlations between certain elements seen in globulars that are not seen in galaxies. Some people interpret that as multiple populations, but there are other non-multiple population interpretations. Okay, so that's one box. Now that we're beginning to look at, but we couldn't look at it in Edge 1 because we only tracked oxygen and iron. So now we've got 8 species chemistry, we can return to this question of whether that just drops out. But what I will say is that there are lots of models in the literature for explaining abundance anomalies that involve physics we don't have in Edge. So if we don't see it, it doesn't invalidate everything. It could just mean that we need to have supermassive star physics or something that's just not in there, right? Also fascinating. So we're going to look at it, but we're not there yet. Yeah, so we're going to look at abundance anomalies with what we've got first. That's coming now. So I've got the data to do it. I just haven't had the time. And then if they're there or not there, we'll look at the next step, right? But the other kind of multiple populations where you actually see distinct main sequence turnoff in the color magnitude diagram, those kind of multiple populations we do actually see in our nuclear star clusters, right? And so actually one of the points we're making is maybe some of these Milky Way globular clusters are actually nuclear star clusters, and they have these very distinctive color magnitude diagrams that actually flop out of Edge, but for our nuclear star clusters.
Okay, Justin, thank you very much for the very interesting talk. So let's thank him again. Just let me remind you that he's going to stay until tomorrow, but he's coming back in August. For those of you that stay around in summer, you will have the opportunity to talk with him more. Okay, thank you.
Number 2, those from the
Yeah, the number 3. Yeah, so Ricardo Beckman is leading. Ricardo Beckman is leading that. So she did all the black hole physics in the New Horizons. So we've taken the black hole model from that and smushed it into Edge. Now we have a slight problem because that model was designed for a low resolution simulation. So it's not clear that it's the right thing to do. So it's not things in there for like subgroup dynamical friction. It's actually quite modern dynamical friction. We're just trying different ones. So 10 to the 3, 10 to the 4. We can't go below 10 to the 3 because that's the part of the but we can go down to 10 to the 3 with dry ions. So well, that's where we're going. So far, we've been putting the black hole into 9.5.